Here is the only thing I'm certain about after 15 years of programming. I don't know much about anything. And even when I believe I understood the concept, it turns out I barely scratched the surface and there are other layers and implications I didn't even consider. Case in point, reactivity. Last week I posted a video comparing Svelte, Solid and Qwik based on some core fundamental ideas, with reactivity being one of them. It was a pretty well received video and I was happy with the way things turned out, but then Miško Hevri, the creator of Qwik, called me out on it. He was nice enough to spend an hour of his time explaining some of his thoughts on reactivity, and it turns out my view on the matter was rather naive. So let's spend the next couple of minutes looking into what reactivity really is and how various modern frameworks are solving this problem. Coincidentally, Miško wrote a detailed article on this subject a couple of months back, and his work is the main source of inspiration for this video. For those unfamiliar with him, Miško is a pretty big name in the industry. He changed the way we were building and thinking about web apps by creating Angular in the past, and he is trying to do it again now with Qwik. Considering his experience, I believe it is safe to assume that his take on reactivity is probably a very informed and accurate one. So what is reactivity? At the end of the day, reactivity is a black box which monitors changes in your app state and updates the UI accordingly.
What's in the box? What's in the box?
Looking at the most basic example, when a button is clicked in a counter component, the internal state is modified. Based on this state change, the framework knows when and how to auto-update the counter value in the UI. From the developer perspective, Svelte is probably offering the most streamlined experience. Whenever the button is clicked, we just increment the counter value by 1, and the framework takes care of the rest. Compare this with alternatives like Solid, where the Signals API is a bit more explicit. Of course, the Signals API is not a deal breaker, but my argument was that Svelte ranks better on the reactivity scale because its developer experience feels just like magic. However, in his article, Miško looks at reactivity from a more hands-on technical perspective. DX is important, but the workload frameworks do behind the scenes to keep the UI and state in sync is even more important, since this can greatly affect both performance and potential lazy loading optimizations. So, following this train of thought, we can rank frameworks based on the amount of application or framework code that needs to run to reflect state changes in the DOM nodes. On this scale, it should not come as a surprise that frameworks like React or Angular do a lot of heavy work in the reactivity process, while solutions like Qwik or Solid rely on lightweight approaches with code targeting the exact DOM nodes that need to be updated. Interestingly enough, the design decisions behind these architectures have big implications, so let's spend a minute looking at the various ways reactivity is achieved in all these frameworks. We'll do this by analyzing a multi-component-based counterexample, which should simulate at a basic level a component tree and some data exchange, both very common in real-world scenarios. It is also worth mentioning that there are 3 main approaches to implement reactivity in a framework. First, you could compare values directly through some sort of dirty checking strategy. A value can be an expression or a virtual DOM snapshot, and, as long as the current version is different from the previous state, a change is detected. Second, frameworks like Angular are using observables which hold specific values and notify subscribers whenever those values change. Finally, signals can be employed to detect and propagate changes, offering a higher level of control. Older solutions such as React have by far the most overhead when it comes to reactivity. Since there is no direct link between state values and associated DOM elements, each state change will trigger an entire rerun of the whole component tree. So when the button is pressed, the count value is updated and all 3 components are re-rendered. In other words, the 3 functions are executed again and the resulting virtual DOM is compared to the previous virtual DOM. Then, through a diffing strategy, the framework detects the changes between virtual DOM implementations and updates the real DOM accordingly. I think that we can all agree that there is a lot of heavy lifting involved in simply keeping a value updated in the UI with React. Imagine having large component trees with interdependent reactive values, and you can probably see that the overhead could easily get out of hand. To put things into perspective even more, let's look at Svelte's reactivity next. Playing with the demo, we can already see that the number of renders is lower than in the React example. This might be a bit misleading since there is some code still being executed when the button is clicked. You can see this clearly by adding breakpoints in the code Svelte runs to detect changes at the component level. When the button is clicked, counter and display are re-executed. However, note that the button component was not re-executed, so this hints to some optimizations in the whole process. The Svelte compiler is performing dirty checking under the hood, but employs some very efficient strategies in this process. On top of that, their behavior subject store reactivity is even more efficient than the compiler-based one, and you can read more details regarding this variation in the article linked into the description. Moving to Vue, they are also rerunning components when changes are detected. As opposed to Svelte, Vue is not using a compiler yet, so all the reactive logic is runtime-based. Vue's change detection is built on top of refs, which are fairly similar to signals. One advantage of Vue over Svelte is that it is using a single reactivity model based on refs, compared to Svelte's compiler and store implementations. Okay, now moving to a different approach altogether, Qwik and Solid are decoupling the reactivity from the component and targeting a smaller unit, the DOM element. Previously, the smallest amount of executed code needed to detect a change was a component. With signals, the component state can be linked directly to the DOM element instead. Changing the signal value will trigger a DOM update without executing the associated component. In Qwik's case, this is even more important because components that don't execute don't have to be downloaded. This is a major advantage considering Qwik's goal of instant loading and lazy code execution. Compared to previous frameworks, Qwik does not require a hydration step on startup. Because there is no hydration step, no code needs to execute, and therefore no code needs to be downloaded. This is a big accomplishment deserving of a video on its own, so stay tuned for that since I'm planning to post more hands-on Qwik content in the future. Finally, on the workload scale, Solid probably sits comfortably in the first place. Compared to Qwik, Solid's signals implementation can perform both value changes and structural updates directly in the DOM. Solid executes components just once, and that's it. After that, everything in your app will be handled by listeners and effects, changing signals values, which, in turn, will efficiently update the associated DOM elements. So, a simple idea such as reflecting state updates into the DOM can have major implications, ranging from techniques used to monitor changes, to the amount of code executed on each change, and to other associated concepts such as hydration strategies and network transfers. If you found this video useful, please consider clicking the like and subscribe buttons, and until next time, thank you for watching.